Hi, welcome to the next lecture in the Introduction to Haskell Programming series of lectures for NPTEL. In the previous lecture, we looked at uh, a fairly complicated data structure, AVL trees. It was an example of a balanced binary search tree. So, the applications of AVL trees are that you can use it to search for an element, you can use it to store elements, and then from time to time you can insert a new element or delete an element from the list, from the structure, or you can search whether an element exists in the uh, structure or not. So, it is used to implement sets, an abstraction of set or dictionaries maybe. Yeah, so you can also extend this to store some keys and associated values, and you can call this dictionary. So, these are in general called dictionary data structures. Today we will look at another, in this lecture we will look at another data structure called heaps, and in particular we will look at something called leftist heaps. So, heaps are a realization of or an implementation of this abstract data type or abstract data structure that you want to maintain, which is called a priority queue. Okay, it is a queue where every element has a priority. So, think of just a normal queue, but everybody gets some token number, and rather than standing in a queue, they all sit in some chairs, and whichever token number gets called first will go ahead in the queue. That would be the normal thing of assigning a priority to elements. But what you need to do is to do is very efficiently pick the element with the highest priority in the queue, right? So, you want to somehow maintain your data structure so that it is easy to get the element with the highest priority or the lowest priority, given depending on the kind of application you have in mind. So, elements exit to the queue by priority. This is the important point, not in the order that they entered. You could have a VIP entering at the very last minute, but they will be allowed to go ahead very quickly, immediately almost. So, each element in the priority queue is a pair PV. P is a priority, V is value. And the priorities are values of some type A belonging to the class ord. So, priorities should be orderable. They should belong a type that admits an order. So, I mean, so just like with binary search trees also, we could have implemented it in terms of keys and values. Here we can implement it in terms of priorities and values, but that will just mess up the code, and it is not it doesn't really break anything fundamental if you only maintain priorities and not the values. Okay, so we will only show the how to maintain priorities. You can add values, etc., and enhance this data structure quite easily. So, we assume that priorities are distinct. Okay, so no ties. Ties are broken by some means, by whoever entered first, maybe. Yeah, tiebreaker is that the time at which, if two VIPs of equal stature enter the queue, then they will be given, the one who entered first will be given priority. And the priority queue operations we want to support, earlier in the binary search tree or in the set abstract data type, we wanted to support operations of insert, delete and search, and then we also extended it to doing union, intersect and difference. Here you want to insert an element into the queue. Insert is something that you want to support, and delete max, this is the other element you want to support. You don't remove an arbitrary element in a queue, in this queue which we showed an implementation of in terms of lists or in terms of two lists. If you insert an element in the queue, you can insert it only at the end. If you if you remove an element from the queue, you can remove it only from the head. In a binary search tree, you can remove arbitrary elements from the queue. But here again, now you can remove an element, but only the maximum element. Okay, you cannot remove an arbitrary element from the queue. This is delete max is not as strong an operation as delete, because delete says you can delete any specified element. Here you only want to say delete the maximum element. So, maybe you can, you don't need to maybe store one way of implementing a priority queue would be to just use a binary search tree and then say maximum element is always the rightmost element in my tree. We already showed how to do delete max in a tree. You could do that, but if you are only doing delete max and not arbitrary deletes, then maybe there are better ways of organizing the elements, and that is what we do in heaps. So here are a few implementations. Unordered lists, insert takes order n time because you just need to do x colon x's. Delete max will take order n time because you have to figure out what the max is and then delete it. Or you could do sorted lists, descending order of priority. Delete max will take order one time, but insert will take order n time because you have to figure out where exactly this element will fit and you have to put it there. AVL trees, you can do insert in order log n time, and you can also do delete max in order log n time. So this is much better because overall, if I have n operations to do, potentially you would be spending order n squared time with sorted list. Potentially you could spend some order n squared time with unordered list, but order n log n time uniformly with AVL trees. We will see heaps as another way to implement priority queues, and here is how you. This is a very nice and interesting data structure in its own right, and it's a very fundamental data structure like trees and search trees and AVL trees. So the idea in a heap is the following, which is that to determine the maximum, it is not necessary that the elements be sorted. Okay, you only need to know where the maximum is. But once you delete the maximum, you need to know what the next maximum is. Once you delete that, you need to know what the next maximum is. So you need to store not just the maximum, but some extra information. But it need not necessarily be. It is not necessary that the whole list is sorted. We need to keep track of the maximum. Also, the possible second maximum to be installed as the new maximum after delete max. The next maximum and so on. Oh, it looks like you might have to maintain the list in sorted order after all, but no. Heaps tell you that you can get away with a different kind of organization, and the organization is what is called max heap. In this lecture, we will look at max heap. Min heaps are analogous. You can either depending on your kind of application, you either do max heaps or min heaps. A heap, a binary search tree is a binary tree satisfying the binary search tree property, which is that the elements in the left subtree are less than the value of the are all less than the root, and the elements in the right subtree are all greater than the root. In a heap, you have the heap property, which is that the value at every node is larger than the value at its two children. That's all. Okay. This is all that you require. In a heap, the largest element is always at the root because the value you cannot have the largest element somewhere below, because then the parent of that node would have a child that is larger. Okay, so that's not possible. So a heap should be the largest value should always be at the root. So here is an example heap 6, 5, 4, 3, 2, 1. Notice that this is not a binary search tree, right? Because 2 lies to the right of 6, and even here 4 lies to the right of 5, etc. I deliberately chose this example to be not a binary search tree, but it is a heap because 6 is greater than 5, 6 is greater than 2, 2 is greater than 1, 5 is greater than 4, 5 is greater than 3. What is the relationship between 5 and 2? What is the relationship between 3 and 4? It could be anything. I mean, of course, one will be greater than the other, but it could be in any order. You don't care about what order they occur in. All you care about is that the parent is greater than both children. That is all. Here is another heap 6, 5, 1, 4, 3, 2, right? Because 4 is greater than 3, 4 is greater than 2, 6 is greater than 4, 6 is greater than 5, 5 is greater than 1. That's another heap because 6 is greater than 3, 6 is greater than 5, 3 is greater than 1, 3 is greater than 2, 5 is greater than 4. So these 3 heaps are also leftist heaps. What is a leftist heap? A leftist heap is one where at every node the size of the left subtree is larger, is at least as much as the size of the right subtree. Okay. Here size of left subtree, size 3, size 2. Here left subtree size 1, right subtree size 1. Here left subtree size 1, right subtree size 0. Okay. So, in all these cases the uh, size of the left subtree at any node is at least as much as the size of the right subtree, that is all. Okay, in a leftist tree, at every node the size of the left subtree is greater than or equal to the size of the right subtree. Okay. So, if I have a tree like this, this is not a leftist heap, because at this point size 0 on the left, size 1 on the right. Okay, fine. So, leftist heaps have some nice property. Let us denote by LR as H length of the right spine, the rightmost spine. What is the rightmost spine? It is this, right. So, that is the rightmost spine. So, length of the right spine, I will call it rightmost spine. Okay. Suppose the tree is of size n and H1 and H2 are the left and right subtrees of H. Now, n is size H1 plus size H2 plus 1 and size H1 is greater than or equal to size H2. So, therefore, size of H2 is less than or equal to, so therefore, you have n is greater than or equal to size of 2 into size of H2 plus 1. So, 2 into size of H2 is less than or equal to n minus 1, size H2 is less than or equal to n minus 1 by 2, but I will approximate it and say that size H2, I will be a little loose and say size H2 is n by 2, okay, or n div 2, floor of n by 2, let us say. Yeah, so this is what we have. So, in a leftist heap, size of H2 is less than or equal to n by 2, and the length of the rightmost spine of H is actually 1 plus the length of the rightmost spine of H2, because you have this, and you have this. You do this and then you do this. Right, LRS of H is 1 plus LRS of H2. So, our claim is that if size of H is equal to n, then LRS of H is less than or equal to log n plus 1. Okay, and this is not difficult to prove, because yeah, let us prove it here. If size of H equals, recall that if H height leftist tree right, leftist tree H size n, and if you have this, then you have size of H2 is less than or equal to n by 2. We will remember that, and we want to show in general that if size of H is n, then length of the rightmost spine is less than or equal to log n plus 1. And you see the log featuring again. If n is 1, then length of the rightmost spine is also 1, because you have a root and that is it, that is the whole tree. So, 1 is log 1 minus 1, log 1 plus 1, yeah, that is fine. If n is greater than 1 and H2 is the right subheap of H, then LRS of H is 1 plus LRS of H2, which is nothing but 1 plus log n by 2 plus 1, because I know that size of, this is by induction. By induction hypothesis, I know that LRS log of right? But log n by 2 is nothing but log n minus 1 and you are doing a plus 1. So, it is just log n. So, you will overall have log n plus 1, okay. So, that is it. So, you can just do it by induction, okay, this is good. So, just as we stored the height of a tree at every node of an AVL tree, with the heap, you should store the size of the heap at every node, right, and then you will have this. So, this is the heap, this is the module name, this is the type constructor, and you have various other, some smart constructors and various other kind of routines. So, you have union, you have insert. So, union is a method by which if you have two heaps, you will create a new heap whose elements are the union of the elements of the two original heaps. You can find max without deleting anything. You can also delete max, okay, and you can create a heap from a list. Yeah, create to list will take you from a heap to a list. Okay, good. So, empty heap is just nil. Yeah, what is your heap data structure itself? There are two constructors, nil and node, and this int denotes the size, okay, and that is it. And just to be a little, just to make sure that I cannot just copy AVL tree programs and call them heap programs, I am reordering the order of the parameters here. I first give the root, then left subtree, left heap, then right heap, okay. So, in AVL trees you had left subtree first, then root, then this thing in the order of the arguments. Here this node will take the arguments in a different order, nothing specific about this, you can reorder these things in any way you want, okay. Is empty of nil is true, is empty of anything else is false, which is fine. Now, let us compute the size. This is exactly like height in an AVL tree. Just a lookup, there is no computation or calculation involved, okay. Size is this, size of nil is 0, size of node s whatever is s, root of node whatever x whatever is x, for nil etc there are no root, okay. So, root is this, and just like you had an is BST or whatever, I can check whether something is a heap, just to just to get some idea of programming with heaps, and not just this thing, I will also ensure that it is a leftist heap, okay. So, what I do is heap of nil is true, is heap of node sx hl hr is, first I will check that s equals 1 plus sl plus sr, where sl is size of hl and sr is size of hr, because I am storing size, I need to check if the sizes that I am storing are coherent, and I will check that sl is greater than or equal to sr, okay. So, that we have the leftist heap property maintained, and inductively I will check that hl is a heap, hr is a heap, and furthermore left heap is empty or x is greater than or equal to root of hl, and right is empty or x is greater than or equal to root of hr, that is it, okay. So, this checks whether something is a heap or not, and it takes time proportional to the size of the heap, okay. Okay. Now, the most fundamental operation I do with heaps is what is called a union. I will take two leftist heaps of size m and n, and I will produce a new heap which is the union of the whose elements are the union of the elements of the original two heaps, and I would like to be able to do it in some good time. Let us see what the time estimate is. I know for a fact that if I have leftist heap of size m and n, the right spines are of order log m and log n. Let me call it some c log m and c log n for concreteness, where c is some constant. I can pick it big enough. Okay, and okay, so the union is implemented by walking down the right spines. This is the idea. Let's see how it works. So because the right spines are of length log m and log n, so it is almost like taking a union of the right spines and adjusting the rest of the heaps somehow. And if I want to take union of two or some kind of merge of the two lists of length log m and log n, it will take log m plus log n time. So this is what it will take. Okay. So okay, while I try to do this, like rebalance that we had to do with AVL tree, the leftist property might be violated, and so in such cases you have to realign. And what does realign mean? Realign of nil is just nil because there is nothing that is violated. Realign of H is a heap where the heap has this pattern node S is the size, X is the root, HL and HR are the left heap and right heap. If size of HL is greater than or equal to size of HR, there is nothing to do, so you just return H. Otherwise, you just swap the left and right subtrees. Okay, if you had this and that was larger than this, so you just swap these two. That's all. There is nothing more. There is no more complicated rebalancing to do because within this is a heap. Heap property is maintained. And then what else do you need to check? There is a root here, there is a root here. Call it x, call it y, call it z. X is greater than or equal to y. In fact, x is greater than y. X is greater than z. And if you are swapping, you just need to ensure that x is greater than z and x is greater than y. There is nothing more to do. So this is all you need to do. Okay. And recursively, this is a leftist heap. That is a leftist heap. These two are leftist heaps. And the overall thing was imbalanced, so you made that the overall heap also a leftist heap. So now at the root level you maintain that size of left heap is greater than or equal to size of right heap. So the overall thing now becomes a leftist heap. And that's basically it. So now you need to do union of H, and if one of the trees is nil, then you just return H, right? Union of nil and H is H. Union of H1 is heap 1, H2 is heap 2, and H1L, H1R are the left and right subheaps of heap 1, H2L and H2R are the left and right subheaps of heap 2, S1 is the size of heap 1, S2 is the size of heap 2, X is the root of heap 1, Y is the root of heap 2. So I need to put X and Y as union. So what is it that I need to do? Okay, so let's take a look at this. I have X, I have H1L, H1R, I have Y, I have H2L, H2R. Okay, so the root, so X is already larger than everything else in its heap, Y is larger than everything else in its heap. So the maximum has to be either X or Y. So if X is greater than Y, you make X the root. But if you make X the root, then you sort of cut out these two things, H1L and H1R, right? What do you do with those? So you made X the root, and yeah, so then you keep this as H1L, and what you do is you go and union. So the right thing will be union. So Y H2 union H1R. That's really what you're doing. Okay. So union of H1 H2 is node H1L x if x is greater than or equal to y, then node H1x union of H2 H1L H1R. Okay, that's what you're doing. You have two subtrees, make one the subtree of X, take the union of the other with the tree H2, right? So that's what you're doing. So union of H1 H2, H1R H2, left subtree is H1L, root is X, and now you have a new tree, but the size is S1 plus S2. So you do this, but now you need to realign because your H1L might H1L is greater than has size more than H1R. But after you do union of H1R with that H2, the sizes may not be the same, so you might have to realign. But once again, if you do union recur inductively, the union of H1R and H2 will be a leftist heap. Only at the root level, you might need to do a swap of the left and right children. That's all you need to do. So that's the thing. So you make a recursive call and you make a constant time operation. Otherwise, you do the other thing. Otherwise, you make y the root. Y's left child will be y's left child, and y's right child will be union of H2R and H1. And this is the point. So you want to do this union thing based on the right spine, because the right spine is the smallest and that has size guarantees of log n, etc., etc. Okay, so this is basically it. Okay, and the realign will take care of doing the thing, but the realign will happen only after you do the union, so you don't need to worry about the time complexity actually. Right, an important heap of other important heap operations are implemented using union. Okay, for instance, insert and delete max take order log n time because of the following. Insert of x and h, insert of x, insert x in a heap h. Right, what do? You create a single node tree, node 1 size, this is the size, x nil nil, and you union it with h, that's it, that is inserting this thing. You will end up with a union, the union will take the union of all the elements, so which means that x is included in h, and it will take time order log whatever the size of h is, and that's it. Okay, and you will still have something which satisfies the heap property. Find max, if the heap itself is empty, then nothing else, just root of h, because the root is the max. Delete max of nil is nothing and nil, delete max of node whatever x hl hr is just x. You take x out, but then you are left with hl and hr, you should union hl and hr, that will form a new heap. Okay, okay, but all these things you can do in order log n time. This is the main takeaway, right? So this is the point, all insert, union, and actually we need to look at why this union takes order log plus order log n plus log m times. Let's go back a bit. Yeah, so recall that if h1 is of type, if h1 let's say is size n, h2 is size m, let us say, then I know for a fact that h1r is size less than or equal to n by 2, h2r is size less than or equal to m by 2. Right. So if I say that my time taken for union h1 h2 takes time some c times log size of h1 plus log size of h2, let us say, right, size log n plus log m. Inductively, let us say that when one of the trees is nil, there is nothing much to do, okay, so it takes constant time, but otherwise if I have h1 and h2 union of, by induction hypothesis I know that union of h1 or h2 will take time log c times log at most c times log n by 2 plus log m, which is nothing but c log n plus c log m minus c, right? And then that c is what you use to pay for whatever work you do, because you did the recursive call of union and then you need to put back some nodes and do one realign operation, that is c, okay. So union of h1 h2 is the time taken is c log n minus plus c log m minus c plus c, okay. So this is the point. If you make the other recursive call, then no issues, it's the same calculation again, because the recursive call will cost you c times log n plus log m by 2, but that is nothing but c of log n plus c of log m minus c, okay. It's the same thing as in the earlier case. So in either case you will have c log n plus c log m minus c for the recursive call, and when you come back up you will add the c, which is the thing here. And how many recursive calls do you make? This is the most important point. The number of recursive calls is at most log n plus log m, because you are descending down the rightmost spine in each tree, and as you descend in the rightmost spine, your size of the tree gets reduced by half every time. So in log n steps you will reach nil here, in log m steps you will reach nil there. So maximum number of recursive calls you will make is log n plus log m, and when you go down till the end and when you come back up you will do realign, that is okay. But so you are doing log n plus log m steps, and on the way back to the top, because once you do the recursion, after the recursive call you come back and do some operations, right? The realign you do on the way back up, okay. Yeah, this is very similar to the realign is the main thing. This is very similar to the merge sort that we saw, where you keep on splitting the original task down all the way to singleton lists, and you just do a merge on the way back up. So this is really what is happening, but you do a realign on the way back up, but the recursion is along the right spines, so there are only log n plus log m recursive calls, okay. Okay, so that does this. So now you have union and delete max and find max all in. Delete max actually is not order log n, it is delete max is order log n. Find max is order 1, okay. So you can do all this, okay. So now this is if you are already given a heap, but how do you create a heap? That is the next question.